Okay, so first we will open Notepad++ and now we will create a new file. So click on this button. Now first we will save this file as .vhd or VHDL file. So click on File, then Save As. Now go to our folder, so that is in UART project, and we have source folder inside it. So like previous, we will save all of our source file in this folder. Okay. Now give some name to this file. Let's give it shift register. So shift register. Now select the file type. So the file type is VHDL. So basic hardware description language. Now click on save. So first we will give the library and package declaration. So give it library IEEE use IEEE dot std underscore logic underscore 1164 dot all. Now this is the time for entity declaration. So give it entity. Now suppose our module name is shift register. So give it shift register is. Now first I will give the generic declaration and then port declaration. Okay. So first write the structure for it. So generic. Now in this section, we will define all of our generics, right? And next is port declaration. So give it port. Now bracket close, semicolon and entity. So this is the basic structure of our entity, right? Now first we will define our ports. So give it. So first I will define the standard inputs. So that is clock and reset. So give it clock. That is input type and std underscore logic. And we have reset, that is in std underscore logic. Now, if you look at the block diagram of UART receiver, then you will see that we have 3 ports inside this shift register. That is shift enable, that is input type. We have D in, that is again input type. And we have D out, that is output type. And also that is having the parallel data output. So define them one by one. So we have shift enable, that is input type and std underscore logic. We have D in, that is again input type and std underscore logic. Next we have D out. So that is output type and this is std logic vector. And now we have to define the range of this D out. So if you are working on the 8-bit data width, then this will be 7 down to 0, right? But instead hard coding this 7, we will prefer to use a generic because RS-232 protocol supports from 5-bit to up to 8 or 9 data bits, right? So I really don't want to hard code this value because if in some other application, if I want to change my data width, then I have to write this code once again. Okay, so instead hard coding this, I will use generic. And let's suppose the generic is data width. So data width minus 1. Okay. So let's define this data width in the generic section here. So this is data width and that is integer type, right? Okay. So that's complete our entity part. Next is architecture. So first we will write the body of this architecture. So architecture behave of shift register is now begin. And in the last and architecture, or you can write and architecture name. So this is behave. Now, because we are designing a shift register, and if you recall from our previous sessions where we have explained the shift register and their functioning and their physical structure. So there we have explained that shift register is actually a cascading of flip-flops. Means output of one flip-flop going to the input to the next flip-flop. Means all of the flip-flops are connected in the series. Output of one flip-flop going to the input of next flip-flop. So for this shift register, we have used registered process block. Okay, so we are doing the same thing here as well. So we will write a registered process block. Okay, so first we will give some name to this process. Suppose the process name is shift process. Now process. Because this is a registered process block, so we will use clock and reset in the sensitivity list. So clock and reset are in the sensitivity list. Next, begin. And in the last, and process. So this is the basic structure of process block. Now we will write the structure for a registered process block. So just write the framework for this registered process block first. So if reset is equals to 1, then do something. Else if at rising edge of clock, then do something, and if. Let me correct the spelling of else if. So it is ELSIF. Now we will write the code for the shift register. Okay. Now we will use one internal signal for this shift register. And suppose this shift register name is SR. So when this reset is asserted, means when reset is high, then suppose our SR signal gets logical high at all of these elements. So SR gets the value of others 1 semicolon. Now first define this SR inside this architecture section. So this is a signal SR, and that is a steady logic vector and having the same range as D out. So let's copy this and paste it here. So we have signal SR, that is a steady logic vector and having the same range as our D out. And at this line, when reset is high, all of its elements gets a value logical high. Okay. Now what will happen when the rising edge of clock is detected? So when we have the rising edge of clock, we need to shift our data. Now the question is that where to shift the data, either towards the left or towards the right. Please note that we are designing a UART communication based on RS-232 protocol. And as I explained that RS-232 protocol sends the LSB first, means least significant bit first. So in this case, we will shift our data towards the right. Don't worry, I will explain it in some time in more details. But before this, we need to understand that we are not going to shift these flip-flop data at all the times when we detect this rising edge of clock, right? Instead, we will only shift our data when this shift enable pin is asserted, right? So let's write this logic first. So when this rising edge of clock is detected, then we will check this shift enable pin. So when this shift enable is equals to 1, then what will happen? We will shift our data towards the right. So our shift register will be D in concatenation with shift register. Now the leftmost value of shift register, so SR left down to 1 semicolon, right? And if. And that's it. Our shift register has been created. Now this is the most important line here in this program. So let me explain it. So what is happening that first we are looking for this rising edge of clock, and then we are detecting this shift enable pin. So at this condition, we will capture this D in at the MSB position. And then we shift the shift register data towards the right by 1 factor. So we have written SR left down to 1. This means that this D in input, which comes from the input ports from here, that will be captured at the MSB of this shift register. And the existing data of shift register moves towards the right. So the 0th index will be moved out from this shift register. So we have this statement. Okay. Now this is fine if you're working on the RS-232 protocol, where you are transferring the least significant bit first. But now suppose you are working on some other project where you are not using RS-232, and at that application you are about to transfer the MSB first. So the question is that how you are going to implement that. Pause this video and think a bit. Okay, so let me explain this, or even let me implement this in this code itself, so that we can use the same code on those applications as well. So what I'm going to do, that I will create a new generic here, which will tell us that either we are going to use MSB as a first bit or first transferring bit, or we are going to use LSB as first transferring bit. Okay, so let's give it some name. Let's mark it MSB or LSB. Okay, and that is character type. And now we are going to use if generate statement for this purpose, right? Okay, so first write the structure for this if generate statement. So first we will give some title name. So suppose this is LSP underscore first. Now write the generate statement. So if MSP or LSP is equals to L, then generate, and in the last and generate. Okay. Now because this code here that we have written it for the LSP first, right? So what I will do that I will move this code inside this generate statement. Okay. So that's very simple. Let me correct the spell here. So that's and generate. Now I will copy this whole code because everything is going to same if I'm going to transfer the MSB first. So what will happen then this MSB or LSB is M. Let's change its name. So that is MSB first. Everything is same. The only difference is shifting operation, right? Because now we are transferring the most significant bit first. So we need to shift our data towards the left by one factor. Okay, so that is very simple. Let's remove this D in from here. So we have this SR, that is SR left -1 down to 0 and concatenation with D in. So what will happen that when this rising edge of clock is detected and we have this shift enable is asserted, then this D in input will be captured at the index 0 of this shift register, right? And all the elements of shift register will shift towards the left by one factor. And that's it. So when you specify that you are going to send the least significant bit first, then this line of code will be generated, or the structure from this code is generated. Or when you specify that you are going to transfer MSB first, then these line of codes will generate the structure, right? Now, one important thing that everything that we have developed that is on this shift register, and that is our internal signal. We have not done anything on this D output, right? So what I will do that I will move the shift register data towards this D out. So this is D out gets the value of SR. So remember all the structure of flip-flops will be generated on this shift register signal. And D out is just like the wiring up those shift register outputs to the output port, right? So if shift register is 8-bit wide, then all of 8 wires will be connected to the 8 wires of D out. Okay, so I think the code is done. So this is our library declaration. This is the entity declaration along with generic and port section. And next we have this architecture. Okay. Now let's save this program. So Control S. Now first we will compile this code for any syntax error, and then we will write a test bench for this shift register, and we will look for the output in the terms of waveforms, right? So for that we will open model sim simulator. So open model sim. Okay, let's maximize this. Okay, so right click. Now click on add to project and select this existing file option. Now click on browse. Now select the source folder from our project, and now you will see your shift register module here. So just select it and click on open. Now click on OK. Now first we will compile this shift register program. So right click and click on compile and compile selected. So you can see that compile of shift register.vsd is successful and it does not have any syntax error. So this is the time to write a test bench for this shift register module. So I will go to the Notepad++ once again. I will create a new file. So Control N. Now again, first I will save this file. So click on File, Save As. Now because this is a test bench, so I will save this in this test bench folder. Okay. And give it some name. This is shift register underscore TB. Okay. Now click on Save. So first I have to give the library declaration, then entity declaration, and then architecture declaration. Okay. So what I will do that I will copy the whole code from here and then just paste it. Okay. Okay. So you can see the details are not same and the keywords are not highlighted here. Just because that I forgot to save this file as .vsd or as an VHDL file. So let's save this once again as .vsd. So this is shift register underscore TB and this is basic hardware description language. That is VHDL file. Okay. Now click on save. Okay. So you can see that we have library declaration and we have this entity declaration. Now because this is a test bench, so we actually do not need this. So let's delete this part. I will keep this generic part here in this entity section, okay? Because I'm going to use this in the later part of this code, okay? And now I will delete all the architecture part from here because we are writing the test bench here in this code. And for this, I will need this entity section of this shift register module. So what I will do that I will use this part of code to define the component, okay? So now this is a component. So this is component shift register is and in the last and component. Okay. And now I have to define all the input output ports as a signal, right? So this is just a standard structure, right? So let's define all these ports as signal. So this is signal clock. Next, this is signal reset. Next, this is signal shift enable. We have signal D in and we have signal D out. Okay. And in the last semicolon. One more thing that we cannot have the same module name in the same project. So let's change to this shift register underscore TB because this is test bench. So this is shift register underscore TB. Okay, so that's look good. Now I will copy this component part from here once again, and I will paste this inside this architecture section after this begin keyword. Okay. So what I'm going to do here that I want to use that shift register component as a block here, right? And I will give the port map and generic map here in this section. Okay. So for this, first I will give the name to this component. Suppose this is UUT or unit under test. Now I do not need this is keyword after this. Now generic map and this port map. Now suppose data width is connected to data width. Okay, and MSB or LSB is connected to MSB or LSB. Okay, and we do not need semicolon here because this whole line of code is treated as a single statement. Although there are multiple lines, but these all line of codes are treated as a single statement. Okay, so there is no semicolon here. Now port map, so clock is connected to clock. Reset is connected to reset. Okay, so reset. Shift enable is connected to shift enable. Now this D in is connected to D in, and this D out is connected to D out. Okay, and we do not need this and component part here. Okay, so that is our component mapping. Now first we will define this data width and MSB or LSB generics. Okay, so our data width is suppose 8 and our character, and I want to send LSB first. So this is L. Okay. Now we will write the VHDL code to drive all of our input ports, right? So we have these input ports in this shift register module. So let's define the clock first. So I'm giving the initial value to this clock signal. Okay. So let's create a clock signal of 50 megahertz first. So this is clock is equals to or clock gets the value of not of clock after 10 nanosecond. Okay, so that is our clock signal. Now we will write the process to drive all other input signals like reset, shift enable, and D in. Okay. Okay, so let's write the process to drive all the input signals or all the input ports, right? So let's give it some name first. So this is tb underscore process. Now this is process. Now I will not write anything in the sensitivity list because we are going to use wait statement for this process. Okay, so tb process colon process, then begin, and in the last and process. And before this, I will use wait statement. Okay, because this whole process will be only executed once. And once this wait statement is triggered, then our simulation will stop here. Okay. Okay, so let's write the code for this process block. So at the initial state means at 0 timestamp, we have reset, that is asserted. So this is 1. Now suppose we have this shift enable, so that is 0. And we have this D in, and suppose this is logical high. Okay, because that is our ideal state. Now I want to wait for 100 nanosecond. Means this reset will be asserted for 100 nanosecond of time period. Okay. So after this 100 nanosecond, first this reset will be 0. And then I will wait for another 100 nanosecond. So wait for 100 nanosecond. So wait for 100 nanosecond. So that's good. Now, this is the time when I need to capture D in one by one based on this shift enable signal, right? And we need to capture this D in 8 times, right? Because we are using the data width of 8-bit, okay? And I also wanted to send this D in at the mid of some Baud period, right? So what I will do that I will wait for another 4.35 microsecond. Now this comes because we are going to use the baud rate of 115200, and that will have the period of 8.7 macrosecond. So this is about the halfway of 8.7 macrosecond. Okay. And now suppose the data is hex 51, which we are expecting to receive as this UART receiver, right? So suppose this value is hex 51, means the binary value will be 01010001. Okay. Now, because we are using the RS-232 protocol, so that is sending the LSB first, right? So this 1 will transfer first, then this 0 will transfer, then this 0 will transfer, then this 0 will transfer, then 1, then 0, then 1, and then 0, right? So let's write this. So wait for 4.3 microsecond. Now this D in will get the value of LSB. So that is 1 here, right? But here we have one problem because this D in can be received at any point of time, and that is not synchronized with your FPGA baud frequency. And if you remember from our shift register module, then this shift enable input is synchronized with your rising edge of clock signal, right? So there is no guarantee that after this waiting period, we also have the rising edge of clock, right? So to drive the shift enable, we actually have to wait for the rising edge of clock signal. Okay. So we will wait until rising edge of clock, right? So what will happen? That shift enable will get the value of 1, means we will asserting the shift enable signal, and this shift enable pin will be logical high for complete 1 clock cycle. Means at the rising edge of next clock cycle, so wait until next rising edge, so wait until rising edge of clock, this shift enable will be logical low. Okay. So for this clock cycle, this will be logical high. And after this clock cycle, for the next rising edge, this will be 0. And then I will wait for another 4.35 microsecond. So wait for 4.35 microsecond. Okay. Now these multiple line of code is just transferring this 1 bit of data. So I have to repeat this whole code 8 times, right? Like this. So instead doing this, what I will do that I will create one another signal. Suppose this is packet data. So define the signal. So we have signal packet data, and that is std logic vector data width -1 down to 0. Okay. Now, because these are signals, I do not need to write the port direction, right? So let's remove this from here. Otherwise, this will give the syntax error here. Okay, now this looks good. So what I will do that I will assign some data to this packet data. So suppose our packet data is 51. Okay, so this is the packet data. Okay, so that is 01010001 means that is hex 51, right? Let's move this. So what I will do that I will use a for loop. So let's see how we will write this. So for I in 02 packet data width -1 loop. So this is for I in 0 to 7 loop because data width is 8. Okay, let's move this further and add loop. Okay, and now because we are capturing the D in input here, and that is depends on this packet data. So I will modify this hard-coded one to this packet data. Okay, so packet data index I. Now because this is 7 down to 0, so this is 7. So this is 7 and this is 0. So when the value of I is 0, we will capture this 1. When the value of I is 1, then we will capture this 0 and so on. And that will repeat up to 8 times. Okay, so that looks good. Let's give a quick look to the code. First, we have this library declaration. Then we have entity declaration, and we also have generic defined here. And we have also initialized the generic values. So data width is 8 and MSB or LSB is L. Means we are sending the LSB first, right? Entity name is correct, so that is updated. Architecture behave of shift register TV is. Now we have the component declaration, so that is good. Now we have defined all the signals. So these signals are coming from these input output ports of our shift register module. And we have also defined one another signal, that is packet data. And the packet data value is hex 51. So it's this value in binary. So here we are driving the clock signal, and that will be generating 50 megahertz of clock signal. Now this process is for driving the input output ports of this shift register module. So we have this reset 1, shift enable 0, D in at the very starting of simulation. Then we will wait for 100 nanosecond, then reset will be 0. And that will be applied for 100 nanosecond. Then after this, we will drive this D in. And for that, we have used this for loop statement. And here we have this component mapping. So we have generic map and we have this port map. So let's save this. And now we will compile it and see if it is having any syntax error or not. So for that, we will go to this model sim simulator, right click, click on add to project and select this existing file option. Now click on browse. Now select our project folder and go to this Testbench folder. So we have this shift register underscore TB. So select this and open. Click on OK. Now we will compile it. So select this file, right click and then compile selected. Okay, so we have this one error. Let's see what it is. So that's saying okay, so there is some spelling mistake somewhere, packet date. Okay, so let's correct it. So this is packet data, Control S for save. Now close this and again we will compile. So compile selected. Okay, so compile of shift register underscore TB is successful. Okay, now we will go to this library tab and we will look for the work library. Okay, so we have this work library here. Now select the shift register underscore TB and click on simulate. Okay, so the simulation window is opening. So I am interested in this UUT. Okay, So I will select the required ports and signals. So I'll need this clock signal. I need this D in, I need this D out, reset, shift enable, and this shift register register. Okay, so drag them into the waveform. Now run this simulation for something around 200 microsecond. So run it for 200 microsecond. Okay, so let's zoom out. Okay, so we have all the pulses generated. So let's see. Okay, so let's change the radix to the hex so that we can easily visualize it. So this is hex and this is hexadecimal again. Okay, so till this 100 nanosecond, we have reset, that is high. Okay, D in is logical high and shift enable is 0. That we have defined in the test bench, right? And after this 100 nanosecond, this reset is deasserted. Okay, so now zoom out a little so that we can see the pulses. So you can see that we have generated 8 pulses here. So this is 0, 1, 2, 3, 4, 5, 6, 7. Okay. Now if you focus on this shift enable, so we have generated this first pulse here. And at this moment, we have captured this D in input. So that is 1. Next value is 0 for the next pulse, then 0, 0. Next 1, 0, 1, 0, right? And that was our data. Okay, so remember we have provided the data hex 51, means the value is 0, 1, 0, 1, 0, 0, 0, 1. Okay, now because we are transferring the LSB first, so first we have captured this 1 here. Next we captured 0, then we captured 0, then 0, then we captured 1, then 0, then 1, and then 0. Now if we expand this D out, so that is our index 0. Now when this first pulse on this shift enable is asserted or captured, then this D in data, that is 1, that is captured by this 7th index, right? And at this second pulse of this shift enable, this D in value, that is 0, now it is captured at the 7th index, okay? And this 1 is shifted to the next index of this shift register, right? And that is happening 8 times. And in the last, when all the data of this D in is captured one by one, we get our data, right? So that is 51. So that's how this shift register works. We provide this D in input one by one, and at the output, we will get 8-bit parallel data, right? So I'm happy with the simulation results now because we can see that is something we are expecting from our code, right? Okay, so let's open the Notepad++ once again. So first we will create a new file. So click on this new file button. Now save this file as .vsd. So save as. Now this time we are going to design Synchronizer for our UART receiver. So we are going to save this file in the source folder, right? So give it some name. Suppose this is sync. Now select the file type. VHDL file means basic hardware description language file. Now click on save. First give the library declaration and entity declaration. So let's copy this code from here and now paste it here. Now this is sync. So entity name is sync. So update this. I will define the generics little later based on our needs. Now we have this port declaration. So we are required this clock and reset signal as an input. So these are okay. Now we need one input as an DIN, which is asynchronous in nature. And we will have one output, which will be the synchronized version of our DIN port, right? So suppose the input port is async, so that is asynchronous, and output is sync out. Okay, so sync out is our output port. Okay, so this is output. Okay, so this is our entity declaration for this sync module. Now architecture part. So architecture behave of sync is now begin and in the last and architecture. So and behave. Okay. Now we are going to design this synchronizer as a two-step synchronizer. Okay. I already explained in our previous sessions that why we are going to design this two-stage synchronizer here. Okay. So for this synchronizer, we will use registered process block. So first we will write the structure for this registered process block. So write it sync process, and that is a process having the clock and reset in the sensitivity list because this is a registered process block. Now begin. If reset is equals to 1, then do something. Else if rising edge of clock, then do something, and in the last and if and the process. Okay, so this is the basic structure of registered process block. And now because we are designing a two-stage synchronizer, so we are needing two internal signals because it will generate two flip-flops connected in the series manner, right? So let's create one signal that is having two elements inside it, or even you can create two separate signals as well. Okay, so what I will do that I will create one single signal, and that will be std_logic_vector type and having the range of 1 down to 0. So we have two elements inside this signal, right? So what will happen that if reset is equals to high, then SR will be logical high on all of its elements, right? So others having the value of 1. Now why we have used 1 here? Because as per the RS-232 protocol standards, we are supposed to get logical high when there is no transmission happening. Means when it is an idle state, it will get logical high. Okay. Now it's possible that in your project, when you are not using RS-232 protocol and you are sending logical low at the idle state, then you have to change this reset condition to 0, right? So instead hard coding 1 or 0, I will prefer to use generic here so that I can use the same code in different application using different protocols. Okay. So what I will do that I will create a generic named as ideal state, and I will move that value into this SR signal. Okay. So suppose this is ideal state. Now I also need to define this in the generic section, right? So this is ideal state, and that is std_logic type. Okay. Now what will happen when reset is not asserted, right? Now because we are designing the system in two-stage synchronizer, right? So at the very first rising edge, after this D input is captured, means this async signal is captured. So at the first rising edge, this will be captured by the first element of this SR signal. So SR0 will capture this async signal, right? And for the next rising edge, this SR1 signal will capture the SR0 signal, right? And that's it. So what these line of codes is doing that when reset is high, you will be getting the ideal state. Else For the first rising edge, when this async is captured, so at the first rising edge, this data will move to the SR 0th index, and for the next rising edge, this SR 0th index will move to this SR1 index, right? So this SR1 index is actually 2 clock cycle delay of this async, right? So in the last what I will do that I will move this SR1 signal into our output. Okay, so that's complete our two-stage synchronizer. And now this is the time to compile our code and check for any syntax error. Okay, so let's save this. Go to this model sim simulator. Now go to this project tab, right click, add to project, existing file. Now click on browse, go to our project. Now select this source folder and we have this sync module inside it. So just open it, click on OK. Now right click and compile. Okay, so compile selected. And you can see we get the message compile of sync.vhd is successful. Means there is no syntax error. So this is the time to write the test bench for our program. Okay. So for this, we will go to the Notepad++ once again. I will create a new file and first I will save this as, so we will use this Testbench folder. Now give it some name. So this is sync_testbench. Now select the file type. So that is VHDL file. So we'll select basic hardware description language. Okay. Now click on save. Now I will follow the same steps. So I will copy this part from here. Now paste it. Now change the entity name. So this is sync_tb. Okay. Now write the architecture. Behave of sync_tb is begin and in the last and architecture. Okay. So now because this is a test bench, so we do not need any port declaration here. And I'm also removing the generic declaration here as well. So let's delete this data. And now we will declare the component part. So for this, I will copy this section from the sync.vhd file and I will copy this here. Okay. And I will also copy it here as well. Now this is a component, not entity. So I will replace this keyword with the component keyword. Okay. So this is our component declaration. And now we will define its input output port as signal, right? So we have this signal clock, we have this signal reset, we have this signal async, and we have this signal async out, okay, in the last semicolon, right? Now first we will generate a clock signal of 50 megahertz. So first what I will do that I will initiate this clock value with 0. And now we will generate the clock signal. So clock will be not of clock after 10 nanosecond, right? And now let's give the port mapping first to this component, right? So this is unit under test. So that is sync. We do not need this is keyword. Now this is generic map. Now because we are working on RS-232 protocol, so this ideal state will be 1, right? So this is 1. Now remove this semicolon from here. Next is port map. So this is very straightforward. So clock is connected to clock. Reset is connected to reset. Async is connected to async. And sync out is connected to sync out. And we do not need this AND statement here. Okay. Now we will write the code to drive our input ports. So that is reset and async here. Okay. So for that we will write a process block. So write it. So give it some name first. So suppose this is tb_process colon process. Now I will not write anything in the sensitivity list because we are going to use wait statement in this process, right? So next is begin, and in the last AND process, right? And before that I will use this wait statement. Okay. So this is the standard structure. So at the very beginning I will apply the reset input. Okay. So what we'll do at the very beginning, reset will be high, and also async, that is our input, that is again high. Okay. Because that is our ideal state. Now we will wait for 100 nanosecond. Okay. And after this 100 nanosecond, we will deassert this reset signal. Okay. So this reset is removed and we will again wait for 100 nanosecond. Okay. And now we are designing the system to synchronize our input signal, right? And because we are using the frequency of 50 megahertz, means the state of clock signal is changing at every 10 nanosecond, right? So here you can see the state of clock is changing at every 10 nanosecond. So we have waited 100 nanosecond here. We have waited 100 nanosecond here. So that's total 200 nanosecond. So there is a possibility that we are getting the rising edge of clock signal after this 200 nanosecond. So what I will do that I will wait for some random time frame. Okay. So for example, I'm waiting for another 3 nanosecond. So that's total 203 nanosecond. So that is not multiple of 10 nanosecond. So this will be a good test scenario, right? So after this total 203 nanosecond, my async output will be 0. Okay. So at the beginning of the simulation, we will have this async is 1, and that is also the ideal state as well. And after this 203 nanosecond, this async will be 0. Okay. So that's it. That's our test scenario. If you want, you can add more test scenarios inside it as well. So what I will do, I will save this file and I will go to this model sim simulator, and now we will compile it first. Okay. So for that, I will add this file. So click on add to project and existing file. Now select this file. So click on browse and go to the Testbench folder, and we have this sync_tb. Now select this and click on open, and now click on OK. Okay. So we can see this sync_tb is listed here. So right click and click on compile, compile selected. Okay. Okay. So we have many errors here. So let's see. Okay. So we have this signal declaration and we have not removed the direction from this port section. So let's see how it looks now. So save this. Now close this. Okay, overwrite. Seems like it's not updated. Okay, let's remove this once again. Now save this. Now go to this model simulation and overwrite. Okay, now compile, compile selected. I think this is not saved. Let's remove it from here. Save, Control S. Now right click, compile, compile selected. Okay, now this is fine. Okay, so that's only one mistake. So we have cleared all the syntax error from our Testbench file as well. Now this is the time to simulate our VHDL code, and let's see the results in the waveforms. Okay, so we'll go to this library tab and we will see this sync_ tab. So right click and click on simulate. Okay. So I am interested in this UUT. So what I need, so I need this async, clock, reset, and sync out, and SR as well. Okay, so let's drag them. And now we will run our simulation for 300 nanosecond. Okay, and I think that is enough time to complete all of our test scenarios. Okay, so run for 300 nanosecond. So let's see. Now let's zoom out little. So let's see what is happening here. Okay, so till this point of time, or till this 100 nanosecond, we have reset and we have async as logical high. Okay, so this is logical high, this is logical high. At this moment, after 100 nanosecond, reset is deaccented, but async is still high. Now after 200 nanosecond, means at this point, this async theta goes to low. So this is high here, and at this point it goes to low, right? And now you can see that our output that is not changed instantly. So this is our sync out. Okay, and that is our output. So that is changing here. So let's see what is happening. So after this change, we are still waiting for the first rising edge of clock signal. So at this point, we will have this rising edge, right? And at this point, this logical 0 from async, that is captured by this 0th index, right? So this is fine, okay? But still our sync output is logical high. It is not changed, right? So now it is again waited for the next rising edge. And at this point, we will get our second rising edge after this async value change, right? So at this point, you can see that our output is also changing. So at this point, our output is logical high. So this is logical high, you can see. And at this point, at this rising edge or second rising edge, our output changed to low, right? Okay. And you can see this value is same as sync out, right? That is changing at the same time. So we can say that our sync out is the synchronized version of this async input. And this sync out that is delayed by the two rising edges of this clock signal from this async input. Although it looks like that the data is delaying by two clock signals, so that will affect the transfer speed, right? But for this RS-232 protocol, that's actually not happening. Why? Because we are using the clock frequency of 50 megahertz, and that is way higher than the baud period of RS-232 protocol, right? So the delay of two clock frequency, that's not affect the speed of transmission here. Okay, so that's complete our synchronizer part as well. So in the next session, we will combine all the elements of UART receiver like shift register, this synchronizer, Baud clock generator, everything, and then we will develop a UART receiver module. Okay, so first we will open Notepad++ as usual. And now we will create a new file, and first we will save this. So file, save as. Okay. So we will writing a source file for the UART receiver. So we will go to the UART project folder and we will select this source folder, right? Now give the file name. So the file name is suppose UART underscore RX for UART receiver. Now select the file type. So file type is basic hardware description language for VHDL. So select it. Now click on save. Now what I will do that I will copy this part of library and entity declaration and I will paste it here so that we can get the framework of library declaration and entity declaration, right? Now remove this generic section from here. We will add generics as per our need for this module little later. Okay. Now coming to the port section. So we will need clock and reset, but we do not need these two inputs here, right? Now, if you remember from our UART receiver module or the block diagram of UART receiver module, then we have few inputs and one outputs, right? So we will declare all the input output ports here in this section. So for this UART receiver module, we will have DIN as an input. So that is input std underscore logic type, and we will be receiving the data at this port. Okay, and we will have one output. So suppose this is dout, that is output type, and std underscore logic underscore vector. So this will be our 8-bit output if we are receiving 8-bit data on this UART receiver port, right? So this will be 7 down to 0, right? But because we are working on RS-232 protocol and it can support different length of bytes like 5 bit, 6 bit up to 8 bits. So I wanted to make this flexible. Okay. So for this, instead this hard-coded 7, I will define a generic and we'll use that generic to define the length of this dout. Okay. So suppose the generic is data width. So data width -1 down to 0. So data width will be 8 in this case. So it will become 7 down to 0. Okay. So let's define the generic first here. So we will have this data width that is integer type. Okay. Also, we are needing 2 additional ports here. One will be input and one will be output. And that will be our interrupt signal or interrupt request, which will be our output type port. And we will have one input which will clear this interrupt request. Okay. So let's define them as well. So let's give some name. Suppose this is RX underscore IRQ clear. IRQ for interrupt request. So this clear port will be our input type and std underscore logic. And we will have one output. So that will be RX underscore IRQ. So that is our output and std underscore logic. Okay. So what it will do that this rx underscore interrupt request will trigger when all the bits are received, okay? And we will trigger it for one clock pulse and then we will clear this signal, okay? And we will clear it by this input signal, that is rx underscore irq underscore clear, right? So that's the purpose of these two input output ports, okay? So we have one more thing to change. So we will change this entity name. Suppose this is UART underscore RX for this module. So I will copy this. So this will be used as an entity as well. And now we will write the architecture for this module. So this will be architecture behave of this entity name is now begin and in the last and architecture or and behave, right? So we have this library declaration. Then we have this entity declaration. Here we have the generic part and we have also this port part, right? And now we are going to use all the modules which we have developed for this UART receiver as per our block diagram, right? So what we are going to use here, number one, that is Baud clock generator. Number two, shift register. And number three is synchronizer. We are also going to write some additional piece of code to interconnect everything in a synchronized manner so that we can get whatever we wanted to get from this module, right? So first we will declare all the components in this module here. Okay, so we are going to use this Baud clock generator. So I will copy this part of entity from here and I will paste it in the architecture section, right? Next, we will be going to use shift register. So we have this shift register code here. So I will copy this entity part from here and again I will copy in the architecture component declaration. Okay. Next we are going to use synchronizer. So I will copy this entity section from here and I will paste it here as well, right? Now because these are not entity here but these are components, so I will change this entity keyword with the component. Okay. So this is a component here. Okay. So I will copy this and I will replace this and entity name with and component. Same here and component, right? Entity. So this is component and this is component. Okay. So now we have declared all the components here in this module. Okay. So let me give a quick brief what Baud clock generator is doing here. Because if you remember that we have designed this Baud clock generator for our UART transmitter module, right? And we were using this to transmit the data one by one. And what this Baud clock generator was doing, that it was generating the pulse that when each and every bit will be transmitted. So this module was controlling the time, or you can say bit period of that module, right? Now, because you are sending the data at some specific time interval that is defined by your bit period, so at the receiver end, we also need to receive those bits at the same bit period, right? Because these are controlled by some specific time. And on that time period only, we have to receive or we have to capture that input data. Okay. So that is why we are using this Baud clock generator module here as well in the receivers module. Now the next module is shift register, right? So what it is doing in the receiver module, so it will convert the serial data that is receiving at the receiving port of this module and it will convert it into the parallel data, which is the actual data that we're supposed to receive at this module, right? Because we are going to receive data one by one at this receiving port and we have to retrieve the 8-bit data from this module. Okay. So this thing will be handled by this shift registered component. Okay. And next is synchronizer. And now this synchronizer will synchronize the input signal that is received at the receiving port with our FPGA baud frequency. Okay. And why this is important? Because we can receive the data at any point of time at the receiving port. So that is asynchronous in nature. So we have to synchronize that input signal or that asynchronous input signal with our FPGA baud frequency. And that's what this sync module will be doing. Okay. Okay. So now this is the time for port mapping of these three components. Okay. So I will copy this part from here and I will paste it here. Okay, so now we will write the framework or we will change the keywords for the port mapping. So that will be written after this begin keyword in the architecture section. So to instantiate the component, we need a identifier name for this component. So give it some name. Suppose this is RX underscore Baud clock generator. Now colon. Now we do not need this is keyword here. Now generic map. Okay, so now we will map the generic. So we have data width, we have system clock frequency, and we have baud rate. So this data width will be our data width, right? So if you remember that our data width is 8-bit. So this Baud clock generator will generate 8 pulses here, right? But if you remember about the RS-232 protocol, which we have discussed, so before it started receiving, it will transmit the start bit first, right? So that start bit will be received first at this module, followed by the actual data, right? So what we need, that we need one extra pulse from this data width, right? So this data width will be data width plus 1 here in this case, right? Now comma, and next is system clock frequency. Okay, suppose system clock frequency is 50 megahertz. So this is 50 megahertz, right? And even let's don't hard code it here. Instead, I will prefer to use a generic for this system clock frequency and baud rate as well, so that we can use this code on flexible system clock frequency and flexible baud rate, right? So let's say this system clock frequency is system clock frequency, okay? And this baud rate is mapped to baud rate of this module, okay? Now we will define these two generics in the generic section or generic declaration section. So this is here. So we have this system clock frequency, and that is integer type. And next we have baud rate, and this is again integer type, right? Okay, so now go down. Okay, so we are here, right? Okay, so this is good. We completed the generic map for this Baud clock generator. So next is port map. So before this, let's remove this semicolon here. Now this is port map. Now first two signals are clock and reset. So these are very straightforward. So clock will be connected to clock and reset will be connected to reset, right? Now we have one input and two output here, right? So let's say that this start signal is connected to the start signal, and this Baud clock is actually connected to the Baud clock of this module. So this will be Baud clock, right? And see, this ready signal is also connected with the ready signal of this port, okay? So now we need to declare these three signals. So let's give some comment here. So let's say declare it, okay? We will also declare this Baud clock, so declare it. And we also need to declare this ready signal, so let's declare it, okay? We will do it later. Now coming to this shift register module. So let's instantiate this shift register module. So give it some name. Suppose this is RX underscore shift register. Now this is shift register. We do not need this is keyword here. Now generic map. Now this data width will be the data width of this module. So data underscore width. Now we are not doing data width plus 1 here, right? Like we did in this Baud clock generator. Okay, because we did this here because we are supposed to receive one start bit additionally apart from the data bits, right? But here I am more interested in the data width or the actual data. So I will ignore the start bit here. Okay, so I do not need this additional bit here. So our data width will be our actual data width of this module. Okay. Now this MSB or LSB, so we know that we are going to use RS-232 protocol, and that will transfer the LSB or the least significant bit first, right? So I will say this is L here for this UART receiver module, right? Well, we do not need to define this as in generic because we know that we are working on the RS-232 protocol for this UART receiver module, right? So I will just straightforward map this LSB to this generic, right? So that's complete our generic mapping. So let's remove this semicolon from here. Now it's time for port mapping. So port map. So what I will do that I will copy these two statements from here because these are standards and I will paste it. Okay. So this is clock and this is reset. Now we have this shift enable. So what this shift enable is doing here, that when we receive this shift enable pulse at this shift register module, then we will capture the input data received at the input port, right? So this is actually the output of our Baud clock generator, right? So what I will do that this shift enable will be connected to the Baud clock signal. Okay, so this will be connected to the Baud clock signal. Now we have this D in and D out. Okay, so this D in must be the synchronized version of our D input. Now, if you remember what we have defined in the entity section for this D in, so which is input type, but this is asynchronous in nature. And for this shift register, we need to synchronize it, right? And for this, we will going to use this synchronizer module, right? So suppose let's give it some name and we will assign that synchronized signal to this D input. Okay. So suppose let's say we have an internal signal that is named as RS synced. So this RX sync will be the synchronized version of our D in signal or D input, right? And our output is very straightforward. So that will be our final output. So this will be connected to D out, right? And that's it. So that's our port mapping for this shift register module. So let's remove this component keyword here. We do not need this. And let's remove this component keyword from this Baud clock generator module as well. Okay. Now let's come to the synchronizer module. So first we will give it some name. So this is suppose RX underscore sync. Okay. Now let's remove this is keyword from the last. Now generic map. Okay. So ideal state. So again, we can define a generic here and then we can map that with this ideal state. But for this RS-232 protocol, we know that our ideal state is logical high, right? So I will map it directly with the logical high. So let's map it. So this is 1. Now let's remove this semicolon from here. Now port map. Okay, so I will copy this clock and reset part from here because these are our standard signals. So these are clock and reset. So clock is connected to clock. Reset is connected to reset. Okay. Now asynchronous. So if you remember from the synchronizer module, then we are receiving this asynchronous signal as an input and we will get the synchronized version of this signal at the output, right? So this async signal is actually our input port of this module and this is D in. So let's copy and let's paste it here at this D in. Okay. And what we will get at the output. So our output will be this RX underscore sync, right? So let's copy this, right? So that's complete our port mapping of synchronizer as well. So let's remove this AND component section here because we do not need this. And okay, so we have to remove this AND component section from here as well and from here as well, right? So let's see what extra signals we need to declare. So we need to declare this RX underscore sync and everything else we had defined here. And everything else we also defined here, right? So everything is good. Now, this is the code which is interconnecting all of these components here in this UART receiver module, right? And we have used a couple of internal signals as well. For example, this start, this Baud clock, this ready, etc., right? But till now, we have not defined that when this start pulse should be given. Means that must be given when we have received the start bit at the reception port of this UART receiver module, right? So for that, we need to detect that start bit for this RS-232 protocol. And how we are going to do this? So we know that for RS-232 protocol, we are supposed to get logical high when it is in idle state, means when there is no data transmission, right? And when there is some data to transfer or when there is some data to receive, then we will supposed to get logical 0 as a start bit. Okay. So basically what we need to do that we need to detect that falling edge on this D input means when we are getting the transition from state high to state low, this means that we are about to receive some data at the reception port, right? So first we will write the code to detect this falling edge on the D input, right? And for that, we will design a registered process block. Okay, so let's go down and let's write a process to detect this falling edge on this D in signal or D input, right? So first we will give it some name. So suppose this is falling edge detection. Now this is a process and because we are designing a registered process, so clock and reset will be in the sensitivity list. Now begin. So first we will write the structure for this process block. So if reset is equals to high, then do something, else if at rising edge of clock, then do something and in the last and if, right? So this is our framework. Okay, so now let's write the logic for this. So how we can detect this falling edge on this D input. So for this, what I will do that I will create a new signal which will be delayed by 1 clock cycle of our synchronized input. Okay. So let's say that signal is rx underscore sync underscore delete. Okay. And this will get the value of rx underscore sync. So basically what this statement will do that it will transfer the rx sync data to this rx sync underscore delete signal after 1 clock cycle. Okay. So now we have two signals which is carrying the same data, but the delete signal is capturing that data after 1 clock cycle. So we can use that thing to detect our falling edge. How? So for this we will use condition. So what I will say that if this rx underscore sync is actually 0 and this rx underscore sync underscore delete, this signal is actually 1, then we will have the falling edge, right? So let's create another signal to detect this falling edge. So let's say this is falling edge detected. Okay. So this will be 1 because we have detected this falling edge, and all the conditions other than this if condition will have falling edge 0. And in the last and if. Now, if you're confused about how we have detected this falling edge with these two conditions, then take a pen and paper and design this, right? So first draw one line and suppose this is 1, okay? And this is rx underscore sync signal, and at this point it is going to loop, okay? So what we have said that we have another signal that will follow the data of this signal but after 1 clock cycle, right? So this is 1. So this is 1 up to here, for example, and after 1 clock cycle it will be 0. Okay, so this is our rx underscore sync signal, and this is our rx underscore sync underscore delete signal, right? Let's map this together. So at this point we have to detect this falling edge, right? Because this is our falling edge here where rx sync goes from logical high to logical low, right? So at this point, you will see that this rx sync is 0, but rx sync delete is high, right? Because for this delete signal, this transition from 1 to 0 will happen after 1 clock cycle. Okay, so we will detect this falling edge here. So that's the condition here. So that is rx underscore sync is 0. So rx underscore sync is 0, but rx sync delete is 1. So we will have this falling edge. So we give it some name. So that is falling edge detected. And for any other situation, this falling edge is not detected, right? So that's the whole story. So let's remove these two lines and I will mark this as a comment that we need to declare it later. Okay, so we'll declare it. And in the last, we will have this and process. Okay. So by using this falling edge detection process, we have managed to detect the falling edge on our synchronized input signal. So now we can detect the start bit, but there is a problem. And the problem is that this falling edge will be detected for all the state transition from 1 to 0, right? And that is our start bit, but that can also have our data bit. So it will detect all the falling edges present in the input signal or present in the input data, right? So we cannot use this falling edge detected signal straight to capture the start bit, right? Because every time it detects 1 to 0 transition in the data signal, it will treat it as a start bit, right? So we need to tell our module that only the first transition is actually a start bit. And after that, we will have our data bits. Okay, so before writing that section of code, let's also give the reset condition. So first I will say that do not detect the falling edge in the reset condition. So I will copy this statement here and I will paste into the reset condition. And I will also say that rx underscore sync underscore delete should have some defined state, right? And I will prefer to choose logical high here because in the ideal state, our RS-232 protocol is about to receive logical high, okay? So our this rx sync delete version or this delete signal will also be logical high, okay? So that's complete our falling edge detection. And now we will write the code for detecting the start bit. And that will be our first falling edge only, okay? So what I will do that I will use a finite state machine for this purpose. Okay, so let's see how we can design a finite state machine. So for this, first I will create a data type for finite state machine. So let's declare it first. So we will declare it inside the architecture and begin section. Okay, so this is the section we will declare. So write type. Now give it some name. Suppose this is state. So type state is. Now suppose we have three different states. So first state is ideal, when we are about to receive logical high. The next state will be collecting the receiving data. So give it some name. Suppose this is collecting Rx data. And we will have one more state, that is all the data bits are collected. So let's name this collected, right? So we have three different states. Number one is ideal. Number two is collecting the receiving data. And number three is all the data bits are collected. So collected. Now we will define a signal based on this new data type. So this will be our signal and give it some name. Suppose we are giving this C state for current state. So this will be our current state, and this is, and that is state type, right? Now go down, and now we will write the FSM to detect the first falling edge only. So that will be our start bit. And after this start pulse, we will trigger our Baud clock generator, which will generate pulses to capture the input data one by one. Okay, so that's the whole interconnection. So first what I will do that I will copy this section of code and I will paste it because I need a registered process block for this finite state machine. Now first I will change this name. So now this is our finite state machine. So let's give it some name. Suppose this is RX finite state machines or RX FSM. Now this is if reset condition. So that's okay. And now just remove this section of code from here. Okay, so now we will define the finite state machine. So first we will write the basic structure of finite state machine with the help of case statement. So let's define the case statement. So case current state is, now this is ideal, then it will do something. Now when it is collecting Rx data, then it will do something. Next, when data is collected, then it will do something. And we will have one extra condition, when others. So everything else will be covered in this when others condition that might come because of any bug or hardware failures or environment or other different scenarios, right? And in the last, and case, right? So that's our case statement. Okay, so now we will define that how our finite state machine will drive, right? So what will happen when the state is ideal? So from moving this ideal state to this collecting Rx data state, we have to detect the falling edge, right? So simply code this. So what I will say that if this falling edge detected is equals to 1, then our current state will be our next state. So that will be our collecting Rx underscore data and if, right? Now we are this collecting Rx data. So we need to tell that from which condition we are about to move from this state to this state. So when we will move? So we will move when all the data bits are captured by this receiver module and we have collected all the receiving bits, right? So if we are using 8-bit data, then we will capture 9-bit including the start bit, and then we can move to this collected state, right? But if you notice on the Baud clock generator module, so here we have this Baud clock generator, we had one output and that is ready. And what it was doing, that this ready signal goes high when all the bits are transmitted, right? So here we can use this ready output to detect that if all the bits are received at the receiving end or not, right? Because it was 0 when there is some transmission of data, and it was high when there is no data of transmission, or in ideal state this is high, right? So what I will say that when we are at this collecting Rx data state, we will monitor the ready signal. So what I will write, so if ready is equals to 1, then we will move to the next state, and the next state will be collected state. Okay, now and if, now we will jump to this collected state. So what will happen at this collected state? So first we need to trigger the interrupt signal or the interrupt request signal. So what I will do that we will trigger this rx underscore IRQ, that will be triggered. So that is 1. And after this current state will move to the ideal state, right? Now because we have inserted this rx underscore interrupt request signal, so we have to clear it as well. So what I will do that I will clear it after 1 clock cycle. So when we are at this ideal state, I will write one additional condition here, and that is if our input, that is rx underscore IRQ underscore clear, if this signal is triggered, means when this is 1, then we will clear this rx underscore IRQ request. Okay, so this will be 0 here. And now and if. Okay, so what will happen that, so first we will be at this ideal state, and now when we detect the first falling edge, then we will switch our current state to this collecting rx data. So we are at this collecting rx data. Now it will collect all the data receiving at the receiver end. Does not matter if it is logical high or logical 0, right? And once all the data is received, means when this ready signal is high, we will move to the next state, and the next state will be collected. Okay, so what will happen that this rx IRQ will be asserted logical high, and our next state will be ideal. So these two things will be happen for 1 clock cycle, because after 1 clock cycle our current state will be changed to rx ideal. And here we will clear this rx underscore IRQ request based on this input port. Okay, so this state machine is detecting the start bit. It is not just detecting the falling edge, but it is only detecting the first falling edge or first 1 to 0 transition, right? But if you look at the Baud clock generator, we have still not defined this start signal, right? So let's define that when this start pulse is given and when this start pulse is 0, right? So this start signal means that when we are about to generate pulses at the Baud clock generator to receive or to capture the input data, right? So if we detect the first falling edge, so that is here, and we are just moving from ideal state to this collecting rx data state, at the same time we have to start, or we have to give this start pulse as logical high, right? So what I will do that I will say that when this first falling edge is detected at the ideal state, then our start signal will be logical high. Okay, now because this is high and we want it to high for 1 clock cycle, so as soon as we move to the next state, so that is collecting rx data state, that should be 0, right? So what I will say that at this state, the very first thing that it will do that it will trigger this start signal to 0. Okay, so this start signal will only be given for 1 clock cycle only, right? Okay, so let's also give the others condition as well. So when our state machine or the current state is not landed into some defined state, then our current state will be ideal state. Okay, and now we will also give the reset condition. So what will happen at the reset condition? So first our current state will be ideal. Okay, so that is here. Our interrupt request signal is 0. Let's copy this. We don't have any interrupt request at the reset condition, and this start signal will also be 0. Okay, so that's our reset condition. Okay, so that's our VHDL code for this UART receiver module, but there are a couple of more things we need to think of, and let me tell you what are those. Now if we move to this Baud clock generator, so this module will start generating the pulses right after this start signal is triggered, right? And if those Baud clock pulses are about to land at the same time for the transmitter and receiver, then the problem is that we won't be able to get the right data at the right pulse, because whatever I will transfer from the transmitter module that will receive at the receiving port, and then we will use the synchronizer because that data is asynchronous in nature. And then after 2 clock cycles, it will be captured by the UART receiver module, right? So it will be a big synchronization problem. So what we will do as a good practice that I should expect to receive the data at the middle of 2 successive pulses, which are coming from the transmitter module. And that will guarantee that we are about to capture the right data at the right bit. So think a bit like this. Let me explain this. Suppose this is clock signal. at this point of time, we are transmitting a bit based on the Baud clock generator, right? And at the same time, we are generating another pulse for this receiver module. So suppose this is receiver and this is transmitter, okay? So if these two pulses are at the same time, so at this receiver, we will not be able to get the right data for this data bit, right? But if at the transmitter, the first bit is transmitted here and the next bit is transmitted here, and if we capture this data, not here, but at the mid of somewhere here, and this data at the middle of something here, so that's guaranteed that we are about to receive the right bit. So this bit will be received at this point and this bit will be received at this point. So there will be no synchronization problem. We would be getting this data 100% correct at the middle of these two successive pulses, right? So this is our bit period and this is also our bit period. And this bit period and this bit period is always same. So that is 1 bit period, suppose, okay? So this is 1 bit period. And also this gap, this time gap is actually 1 bit period. Okay. So actually the bit period is actually same for both transmitter and receiver. But what we have to focus on this first bit. So what will happen, this first pulse, that first pulse, if we manage to trigger this pulse at the receiver at half of bit period. So suppose this is half of bit period and then all the pulses after 1 bit period, then our purpose will be solved. Right? So we have to write this additional logic for our receiver module. And that can be only happen from the Baud clock generator module because we are using that for generating these Baud clock pulses, right? So what I will do that I will move to our Baud clock generator. So this is our Baud clock generator module. And here we can see this bit period process where we are defining the bit period of our pulses, right? But the problem is that we have also used this bit period or this Baud clock generator module into our transmitter module. And that logic is also correct. We are needing just additional logic for our receiver module. And that is the bit period for the first pulse must be half of our bit period, right? So we cannot modify this whole program or this whole module for the UART receiver module because that will affect our UART transmitter as well. So what I will do to differentiate between transmitter Baud clock generator and receiver Baud clock generator, well, we can have two options. Number one, you can create a separate module for this Baud clock generator for the receptor or for the receiving module, that is UART_RX. But because these two modules are inside the one big module for the UART transmitter and receiver, so if you write the another Baud clock generator module, so that will generate additional resources on your physical chip. So what I will do that I will prefer to change our existing logic for this Baud clock generator to make it flexible for the RX receiver module as well, right? So first we need to differentiate it that it is working for a transmitter or for a receiver, right? So for this, I will create another generic that will tell either this module is for receiver or for transmitter. So we can use a simple Boolean generic. Let's give it some name. Suppose the generic name is RX true or false. Okay, so this is Boolean type. Okay, now I can use this RX_true to define that if it is working as a receiver module or for a transmitter module. So let's see if this is true, then this is a receiver. Else means if it is false, then it is for transmitter. Okay, and now I will also create one constant for half a bit period. So we have a constant and that is half of bit period, that is integer type, and let's copy this. So that calculates our 1 bit period, right? So the half bit period will be divided by 2 or this baud rate multiplied by 2. Okay, so the system clock frequency will be divided by twice of baud rate. So we will get this half of bit period. Okay. Now coming to this bit period process. Now remember that I have said that all the other pulses except the first pulse will continuously follow the 1 bit period. I mean 1 full bit period, right? And that is 8.7 microseconds for the baud rate of 115200. So we need to only control the first pulse of this Baud clock generator, and that will be half of the bit period. Okay, so these line of codes, So that will be absolutely same, because for all the other pulses other than the first pulse, it will calculate 1 bit period for one pulse, right? So for the first pulse, I will modify our code here. So what I will say that if our generic, so what was that? So that is rx underscore true. So if this rx underscore true is equals to true, then do something else. We will have this bit period counter that is 0. Okay, so that is and if. So if this rx underscore true, then our bit period counter will be half of the bit period. So we have defined the constant for this, or even we can use this bit period here and we will divide it by 2. Okay, so that will also work. So we do not need this, I think, because that will work. Okay, so now I hope this should solve our problem between the receiver Baud clock generator and transmitter Baud clock generator. Now because we have changed its generic, so we need to update our transmitter module and our receiver module as well. So let's quickly update those modules. So this is our UART underscore transmitter. So we must use Baud clock generator here. So this is our Baud clock generator and we are about to use this additional generic here. And we also need to look about the instance for this Baud clock generator. So this will be false here in this case, right? So that is our transmitter module. Now let's update our UART receiver module. So we need to look for the Baud clock generator component. Now let's update this. So rx2 is Boolean. Now let's move to the instantiation. We also need to update this here. Now this is view. Okay. Okay. So that's everything is done. Now this is the time to define or to declare all the signals we have used in this program. Okay. So we have this start. Okay, so let's define a signal. So this is signal start, that is std underscore logic type. Let's copy it. We need to use this statement multiple times for multiple signals. Let's see what else we have. So we have this Baud clock. Okay, so signal Baud clock is declared. We have this ready. We will declare this as well. What else we have? We have this rf underscore sync. So that is again std underscore logic. Okay, so that's good. What else we have? We have this falling edge detected. So let's declare it. Okay, anything else? Let's quickly look over it. Okay, so we have this rx underscore sync underscore delete. We also need to use this and everything else is defined. Okay. So let's replace this. And we do not need this now because everything is declared. I think we are good to go. Okay, let's save this UART underscore transmitter as well, Baud clock generator and UART receiver. So now we will open Model Sim Simulator and first we will compile our code to see if it is having any syntax error or not. Okay, so we will open Model Sim Simulator. So this is our Model Sim Simulator. Okay, let's maximize this. Now because we have updated this Baud clock generator module and UART underscore transmitter module, so we need to compile both of these modules once again. But before that, let me quickly add this UART receiver module into this project. So click on add to project and then existing file. Now click on browse. Okay, so select the UART project folder. So we have our file inside this src folder. So select this and we have this UART underscore rx. Select this, click on open and now click on OK. Now we will compile all of our module at once. So I will right click here and then compile all. Okay, so everything is good except this UART underscore receiver. So let's double click on this error. Okay, so let's see what are the error. Okay, so we have declared the rx underscore sync. Okay, so we have defined this as a signal, so we cannot instantiate with the same name. So let's give it some name, component. Okay, component. So let's save this. Now close, recompile. Okay, we still have one error. So what it is saying? Okay, yeah, we have a couple of extra lines. Okay, let's save this once again. Now let's compile. Okay, so compile of UART underscore rx.vsd is successful. So our VHDL code is clear from any syntax error. So now this is the time for writing a test bench for this UART receiver module, and then we will test it. Okay. So now this is the time to write the test bench for this module. So as usual, first I will create a new file. So click on this button. Now save this file as a VHDL file. So I will go to this UART project. And now we are writing a test bench. So I will choose this test bench folder. Now I will select the file type. So this is VHDL. So basic hardware description language I have to select. Now I will give it some name. So suppose this is the test bench for UART receiver. Okay. Now save. Now I will copy this library declaration and entity declaration from here, from our UART underscore receiver module, and I will paste it here. And I will update the entity name to TB. Now I will copy this. I will use it here. And sorry, it is not pasted, I think. Okay, this is not copied. So this is our AND entity, and this is our architecture body. So let's complete it first. So begin and add architecture. So this is and behave. Okay, so that's good. Now we need to define this entity as a component here in this architecture section. So I will copy this and I will replace this entity with component and this entity name with component. So this is a component here, and I do not need any generic and port here in this entity for this test bench. Okay. Now I will declare all the signals used in this UART receiver module. So these are the signals here. So let's declare them first. So these all are signals. Signal. This is again signal, and the out is also our signal. Because these are signals, so we do not need to write any direction here, because these will give the syntax error. So let's remove everything related to direction, and we will also instantiate this clock, or I will give some initial value to this clock, because I want to generate a clock signal of 50 megahertz. So what I will write that this clock is actually not a clock after 10 nanoseconds. So that will generate a 50 megahertz of clock signal for us, right? And next, first we will instantiate the component for this test bench. So I will copy this part and let's instantiate it. So this will be our UUT, unit under test. Now remove this is keyword. Now generate map. So this will be very straightforward. Our data width. So our data width will be 8 for this module, for this receiver module. Our system clock frequency will be 50 megahertz, and our baud rate will be 115200. Okay, so remove this semicolon from here. Now port map. This is very straightforward. Clock is connected to clock. reset is connected to reset, comma, din is connected to din, Rx IRQ clear will be connected to the same signal. Rx IRQ will be connected to the Rx IRQ, and dout will be connected to dout, right? And we do not need this last statement, so let's remove this. Okay, so that's good. We have instantiated our unit under test, and now we will drive our input signals, right? So for this, I will use a process block. So first I will write the structure for this process. So give it some name. So this is our test process, and this is the process. And now I'm not writing any port or any signal in the sensitivity list because I'm going to use the wait statement here in this process block. Okay, so process now begin. In the last, we will have this wait statement, and in the last, and process. Okay, so that's good. So first I will trigger the reset condition first for the 100 nanosecond. Then I will release the reset condition for another 100 nanosecond. And then we will start receiving the data on the D inputs. Okay, so first the reset condition. So our reset will be high. Also, I want our din to be in ideal state. So din is high. And let's say this Rx IRQ clear, that is also 0 here. Now I want to wait for 100 nanosecond. And after this 100 nanosecond, this reset condition will be removed. So reset is 0. And I will wait again for 100 nanosecond. Okay. Now after this point of time, I will receive the start bit at the receiving point. So our din will be 0. And then I will wait for the 1 bit period. And the bit period is 8.7 microsecond for the baud rate of 115200. So I will wait for 8.7 microsecond. And now I have to transfer 8 bits one by one. And that will be our actual data that we are going to receive at this UART receiver module, right? So what I will do that I will create another signal, that is signal, and let's say this is our data which we are going to receive, and that is std logic vector. Now let's say this is 7 down to 0, and let's remove this 7 down to 0. Okay, this means we are about to receive 8-bit data, right? And let's say our data is, this data is 10101010. Okay, so this is AA in hex. Okay, so this is our data which we are going to receive at this UART receiver module. Okay, so what I will do, so one thing what you can do, that you can write that din will be our data index 0, and then wait for 8.7 microsecond. Then again you can copy this, paste this multiple times, and then you can update this one by one. So that's one thing you can do. Now we are sending this index 0 first because this is our LSB. So this is 7 and this is index 0. And RS-232 protocol sends the LSB first. So first this 0 will be received, then 1, then 0, and up to this MSB. Okay. So as I said, you can use multiple statement for this, or you can just use a for loop for this purpose. So what I will write that for I in 0 to 7 loop. Now I will use these two statements here, and finally and loop. And now I do not need all these statements copied 8 times, right? Now this din will be, okay, so that was our start bit. So let's leave it 0. I will use my for loop from here. So for I in 0 to 7 loop. Now these two statements and then and loop. So now you do not need to copy these two statements 8 times here. So what I will do, that this data 0 will be replaced by data I. Okay. And now once all the 8 bits are received, then we will have the stop bit, right? So din will be 1 for the stop bit or for the ideal state, and I will wait for another 8.7 microsecond, right? So now once we have received this start bit followed by the data lines and then stop bit, we will generate the interrupt request signal, right? So if you go to the UART receiver and if you look for the finite state machines here in the last, so you will see that when all the collection is done, then we will trigger this RX_IRQ, right? And this will be cleared when we insert this RX underscore IRQ underscore clear signal, right? So what I will do that after this, I will clear this RX underscore IRQ underscore clear signal. So this will be 1. And now I wanted to give this clear pulse for 1 clock cycle. So what I will do, so I will wait until rising edge of clock. And once we have this rising edge of clock, then this RX clear will be 0. Okay. I also wanted to synchronize this RX IRQ clear signal with the rising edge of clock, because we do not know that when this 8.7 microseconds will be completed, if that comes at the rising edge of clock or not. And because everything is synchronized with the rising edge of clock here in the receiver module, so we have to wait for the rising edge of clock here before clearing this message or before clearing this signal. Okay, so I think everything is done. Let's save this file. Okay, we have the signal without the semicolon. Let's give a semicolon and then save it. Else everything looks good to me. Okay, let's save this and open this into the Model Sim Simulator. So again, right click on Add to Project and Existing File. Now click on Browse. Now go to this UART project. Now we have Testbench to load this time. So I will click on this Testbench folder and I will select this UART underscore receiver Testbench. So let's rename this. I think what I have saved this. So UART receiver. Okay, so let's save this once again. Save as underscore Testbench. Okay. Now we have the correct file. So let's save this, go to the Model Sim Simulator, and we would be able to see this UART underscore RX underscore TV. Okay. Now open this file. Now click on OK. Okay. So we have this file listed here. Now right click, compile, compile selected. Okay. We come up with few errors. Okay. So it is complaining at line number 30 and 31. So let's go to 30 and 31. Oh, okay. So we have copied the signal declaration in between these two lines. So we have missing component section. So we need to add this component here and then we can declare the signals. Okay. Okay. So let's save this and close this. Once again, we will compile it. So compile selected. Again, we have few more errors. Okay. Let's see what's the problem. Okay, too many things. Control S, save. Now close this, recompile. Okay, so here you go. Our compilation of this UART underscore receiver test bench is successful now. Okay. So now this is the time to simulate our test bench in the forms of waveforms, and we will see that everything is working as per our expectation or not, right? So we will go to this library tab. We will look for the work library. So it is at the top. So we can see this UART underscore receiver underscore TB here. So I will right click here and then click on simulate. Okay, so we have this waveform window here. So I am really interested in this UUT, that is unit under test. And now I will select the important signals that are useful for our analysis. So I will select this clock. Well, let me select all the signals here. So we have this Baud clock, and I will select this. Okay, and everything else. Okay, so these are the signals I'm interested. Let's drag them into the waveform and let's simulate our program for 200 microsecond. I think that will be enough time for generating all the pulses and capturing all the input bits. So run for 200 microsecond. Let's see. Okay, so let's zoom out and let's see if we are getting pulses or not. Okay, so we can see that signals are changing. So we have enough data. So first, what I will check that are we capturing the data in the middle of bit period or not, right? So for this, what I will use this Baud clock. Okay, and I will use this DIN or this RX sync even. So this is, I think, better to take in. Now let's zoom out a little. Okay, so let's see. Okay, so we have this Baud clock as a first pulse here, and then we are generating multiple pulses. Okay, right. So what we have said that we are expecting to see this first pulse of this Baud clock at half of the bit period and all the successive pulses at full bit period. Okay, so first let's quickly compare the time gap between the two pulses. So this is our first pulse. Okay, so now I will add a marker at the first pulse, and that should be around 4.3 microseconds something, because 8.7 microsecond is our 1 bit period. So the half bit period is around 4.35, right? Okay, so let's zoom a little more so that we can see a little better. Okay, so this is the triggering point, and this is our starting. Okay, so that is near about 4.35 or 4.36 microsecond. So that's good, because I think we need to adjust it a little more, but I think this is 4.35, so that is under the acceptance variations. Okay, so that is fine. So we are getting the first pulse at near about half of the bit period, so that is 4.35 microsecond. So that's good. Next we will look over the successive pulse. So let's move this here and let's move this marker here. So that should be near around 8.7 microsecond. Okay, so you can see that we are around 8.7 microsecond. So this is one complete bit period. Okay, and all the successive pulses looks to be at 8.7 microseconds, right? Okay, so these gaps, this gap are identical. So every gap is identical except this first one, because this first one is half of the bit period. Okay, so that's good. Now we will see if we are capturing the inputs at the middle of the Baud clock or not. Okay, so if we look at this of this first pulse, so this is our Baud clock and this is our input signal that we are going to capture. Okay, so this is 0 here, so that is good because that is our start bit. And next we are going to capture this. So this is 0 that we have captured here. So that is good again, because if you remember that the data we have at this test bench, that is 10, 10, 10, 10. So the 0th index or the least significant bit is 0, right? So this, at this point, we are getting the start bit and that is 0. And at this point, we are getting the least significant bit and that is again 0. But when we are coming to the next pulse, so that is next pulse, and here we are receiving 1. So that is correct because the first index of this data is 1. Okay, so that one is received here. Okay, and if you see that we are capturing this input data at the middle. Okay, so we are not capturing it here, but we are capturing it here. So that's a good thing because we are getting this time frame or this time window for stabilizing the input data. Okay, so that's what we wanted from our receiving module. Okay, so that we wanted to capture our input signal at the middle of the Baud period. Okay, so that is good. Now we will see that if we are getting the correct output or not. That means we have captured this 10101010, and that should be received at this output port, that is D out. So let's see if we are getting this data at the output D out or not. So this is our output D out. So let's move it down and let's change this radix to hexadecimal so that we can easily visualize. So we are getting 9F, but we are expecting to receive this data, that is AA 10101010, but we are getting something else. So something is not good. So let's figure out why is so. So what I can see that we are expecting 9 pulses at this Baud clock because we have generated 8 pulses here. And if we go to the UART receiver and if we see the Baud clock generator, so that is data width plus 1 and the data width is 8. Okay, so that's should be 9, but we are receiving 1, 2, 3, 4, 5, 6, 7, 8, 9. And if you see that we are getting AA, so that's what we are expecting after the 9 pulses, but we are getting 3 extra pulses here. So we need to figure out that why we are getting these 3 extra pulses. So if we go to the Baud clock generator, and these are the signals that triggers Baud clock. So let's see what's wrong with the signal. So let's move start at the last and ready at the last as well. Although this is output, so nothing changes. So main thing is the start. Okay, I can see some problem here. So if we notice, then we have one extra start pulse triggered here. So this is good. We are expecting to have this start pulse at the starting when we are about to receive the start bit. But why we are getting this start bit here or this start pulse here? So let's zoom a little. And okay, so we can see some problem here. Okay, so if you see, we are at the ideal state. Then we are going to this collecting RX state, so that is good. But we are getting this start pulse here once again, so that is wrong. So this is triggered here. And if we go to the code, so this start one can only be triggered at this point. So when this falling edge is detected at the ideal state. So at this point, we are at ideal state because the changes will affect after one rising edge. So these changes are here. So at this point, we are at the ideal state. And we are also detecting the falling edge at the data. Okay, so that is also triggered. So that is falling edge is high because that will go low after one rising edge means here. So at this point, this is again high. Okay, let's move to the Baud clock generator and let's see quickly what I will do. That I will remove everything here. So delete. And this time I will go to this Baud clock generator and I will move all the signals to see what is happening. That is the simplest way of checking that what's the problem, because we know that there is some problem in the Baud clock generator, right? So what I will do that I will restart my simulation. So I will click on this button. So that will restart everything. And now I will run my simulation for again 200 microseconds. Okay, so let's zoom out so that we can see everything. Okay, so what is happening? So we are getting this 9 pulse, so that is good. 8 pulse, 7 pulse, 6 pulse, and then we have triggered this start signal. And the counter again reset to 9. So that is why we are getting 3 extra pulses in the output. Okay, so we know that what is the problem. So we will go to our codes and then we will open this Baud clock generator and let's see if we can do anything to solve this problem. Okay, so pulse control, if start equals to 1, then we are generating pulses. Okay, so it looks like that changing anything here will complicate our transmitter module as well. So instead changing here, what I will do, I will go to the receiver module and I will go to this finite state machines. Where is UART receiver? So this is our UART receiver. I will go to this finite state machine. Okay, so what I will do that I have to be extra careful while moving from this ideal state to this collecting RX data state. So what I will do that I will trigger the pulse, this start pulse, when this falling edge is detected, else this start will be 0. So all the other conditions, this start will be 0. And when this ready signal is 0, then only we will move to the next state. Okay, if and if, right? So what it will do that it will restrict the current state moving from ideal to collecting RX data when ready is 1, right? Sorry, when ready is 0. Okay, so that was happening that we were at ideal state, right? And then we detected this falling edge and at the same time we jumped to this collecting RX data. And at this point, we still have ready is equals to 1. And because of this condition, it feels like all the data bits has been collected. So this statement gets triggered and we move to this when collected state. And then we jump to again ideal state. So that was the cycle that was happening here. So to fix this, we have added another condition that if ready is equals to 0, then only we will shift to this collecting Rx data. Okay, so hopefully this should solve the problem. So what we will do, we will go to this waveform once again, restart everything. Okay, and okay, so I think we need to compile first. So let's right click and then compile all. Hopefully everything is good. Now we will go to this library or simulation and we will select this unit under test and we will select everything. Okay, now let's drag everything into the waveform and run it for 200 microsecond. Okay, so let's see. First we will check the Baud pulses because there was some problem. Now we will see if we are generating 9 pulses or not. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so still there is some problem. Okay, so let's see what we are not expecting the problem this time. Okay, I've saved this. Okay, so let's see. I think we have corrected this. So this is Baud clock. So we should be able to see 9 clock signals or 9 pulses. So this is 1, 2, 3, 4, 5, 6, 7, 8, and 9. So this is good. Now I will see this Rx underscore sync. So that should be changing at the middle of bit period. So that is changing middle of the bit period because these are 2 successive pulses. And you can see that everything is changing at the middle of the bit period. So this is good. We have already tested the bit period. So this is the half bit period, that is 4.35 microseconds. And this is 8.7 microsecond. So this looks good. And now we will check T out. So this is expected to be AA in hex. So let's change the radix to hexadecimal. So at the last pulse, we are detecting AA. So that is 10101010. So that is good because we are expecting to see this data because we have passed this data at the receiver. So this is good. Next, we will check this IRQ and IRQ signal. So this should be triggered at the last pulse when this data at the output is generated. So we should be able to see AA here, and that should be cleared after giving this IRQ clear pulse. So that is clearing after this IRQ clear pulse. But somehow we are detecting this IRQ once from the starting, although we are expecting to see this after collecting all the data, because if you look at the code of this UART receiver, then the only state that can change this Rx IRQ to 1, that is collected state. And once we are here, then after 1 clock cycle, when we are reaching at this rising edge of clock, we should be clearing this because of this input signal or this input port, right? So the question is that why this Rx IRQ triggered to 1 before reaching to this collected state? So that is not possible. So let's look when it is changing. Okay, so that's is changing at the starting. Okay, so this IRQ is going to 1 at this point. So till here it is 0 and now it is 1 at this point. And if we look at the current state, because that is the only signal that can change this Rx IRQ, and definitely we have some problem here because initially we are at the ideal state, so that is good, but somehow it is able to manage to go to this collecting Rx data state, and then after 1 clock cycle, so this is the rising edge, it is moving to the collected state, and then for the next rising edge, it's again going to the ideal state. And here we are triggering this Rx IRQ. So definitely there is something wrong. So we need to figure out that why this is the problem. Okay, seems like the problem is because of this reset condition, because that is go down at this falling edge of our system clock frequency. And because of this, we are triggering to this collecting data state, right? Because at this point, our ready, so this ready is high. So till this point, this is low, and after this point, this is high. So this will be applicable at this rising edge. Okay, so let's move to our UART receiver module and let's see what we can do. And even though this is controlled from the Baud clock generator, so even though we can look for the Baud clock generator, and I think we can improve this from this module here. So we will look over the when it is here it is functioning. So you can see that this is working here where we are controlling this ready output. So if reset is equals to high, then ready is 0. So we can replace this 0 by 1. And now we should not see the scenario that is looking here. Okay, so let's save this file. So that is Baud clock generator. So let's save this. Now go to this project. Now compile all because everything is dependent on this. So there is no syntax error. That is good. Now go to the simulator and waveform. And I will restart this. So let's restart everything. I will go to this unit under test of UART receiver. And let's delete everything here as well. So let's select all the signals. So Baud clock, this, and select everything or select all the signals. Let's drag them here in the waveform and run our program for 200 microsecond again. And let's see if the problem is solved or not. Okay, so let's go to this point, adjust the zoom area. Okay, so let's calculate the pulses first. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is good. And let's see the sync data. So that is coming or that is captured at the middle of bit period. So that is good again. Now let's look at the output. So that should be AA at the output when all the pulses has been captured or all the bits has been captured. So that is AA. So that is good. Now look for the RX IRQ and RX IRQ clear. So this looks better now because that is 0 now since starting, and when all the pulses are captured and we can see them at the output AA, then only this RX IRQ or RX interrupt request is triggered. And when we have given this RX IRQ clear signal or at the input port, then we have cleared this RX IRQ. So that is good. Now let's go to the starting because here we see multiple problems. So let's see if that is fixed or not. So we are at this ideal stage. So that is good. And we have this reset condition for 100 nanosecond. And after 100 nanosecond, we have removed this reset condition. So after this reset condition is removed. Then we have waited for 100 nanosecond once again. So we have this 200 nanosecond point. Okay, so that is good. And till this point, we have at the ideal state. So that is good. Now we are expecting to receive the start bit at this RX_sync. So we are getting this start bit here at this point. Okay, so that is good. So for the next rising edge, we have ready signal. So that is good. 1 again. Now the start signal is triggered here. So that is good now. So when this start pulse is given, we have moved to this collecting RX data after this transaction. So that was causing the problem. So now we are waiting for one more clock cycle to move from ideal to collecting RX data state, right? So this is improved. So that is good. And now this collecting RX data state remains continuously until all the 8 bits is received and captured. So here all the 8 bits has been received and captured. And once we have the output that is AA that we are expecting to receive, then we have moved to this ideal stage. And we have also triggered this IRQ request, interrupt request signal. And when we have this clear message or clear signal, then we have removed the IRQ request interrupt signal as well. So this is good. And now I am satisfied with the results. So you have seen that we have changed many things in multiple modules. We have adjusted our Baud clock generator to work with the transmitter module as well as a receiver module. We have fine-tuned our finite state machine as well to fix the bugs that are unexpected, or even we have not think about those problems. So when we were simulating them in the terms of waveforms, we come to know multiple problems one by one. And then we have digged it down that what signal or what triggers are causing those problems. And then we have fixed them one by one. So this session is a good example that how we can see unexpected things in our results and how we need to think to fix those issues. So that's complete our UART receiver module as well. And now this is the time to compile both UART transmitter and UART receiver in a one single module, so that this module is capable of transmitting the serial data and receiving the serial data over the RS-232 protocol. And we will do this in the next session.